Hello. This lecture will cover pages 19 through 28 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on representing sine and cosine waves mathematically, chapter 6D. Before we end this chapter, or before we cover the final topic in this chapter, I want to introduce something that we're going to cover in a couple weeks a second time, but I want to introduce it right now in this lecture. It's on page 19 of your lecture notes, representing sine and cosine waves mathematically. I want you to take a look at pages 306 through 308. In my textbook, it basically is this right here. It starts out with simply sinusoids. Let's see if I can't find it. That's what you're going to look for. You're going to look for this part of the book, sinusoids. But if you follow my lecture notes here, I think it'll cover that pretty well. Sinusoids are a group of AC signals that follow a sine or a cosine function at time. So up to now, we've been talking about DC values. We've been talking about a constant DC value of current or voltage, but now I'm going to introduce sinusoidal waveforms. I want you to note, sinusoids are the only waveforms whose appearance is unaffected by the response characteristics of resistors, inductors, and capacitors. What that says is if you have RLC elements in a network, if you have a sinusoid that's forcing the function, that is the source of the voltage or the current, all other waveforms in that circuit, current and voltage, will also be the sinusoid as well. If V of t is equal to V max sine of omega t, this is an expression here for voltage, where omega is equal to 2 pi f, which we're going to call angular velocity in radians per second. Now this is new to you, but I want you to realize that this is a general expression for voltage. Voltage with respect to time is equal to V max, that's the peak value, times the sine of something called omega t. And omega is referred to as the angular frequency or angular velocity, and it's in radians per second. If this is the value of voltage, then the current can be written as I max sine of omega t. The same form. There are three choices of units used to measure the horizontal axis when we represent voltages and currents, the sinusoids, this way. If you look at the next page, time, you've seen this before, where you have a sinusoidal waveform and then the horizontal axis is represented in terms of time. Or degrees or radians. This axis here can be in degrees or it can be in radians. But I want you to concentrate on this particular figure down here, because what we're going to do is I'm going to introduce this angular velocity, and I'm going to do it this way. Over on the left-hand side here, we're going to put what we call a radius vector. And I'm going to start that radius vector out horizontally, coming out here. And the magnitude of that radius vector is the peak of the waveform over here. So keep that in mind as we rotate this in a counterclockwise direction. This radius vector rotates in a counterclockwise direction continuously. That's the frequency. That's the radian frequency. One cycle is 360 degrees. A second cycle is another 360 degrees. What we're going to do is a way to illustrate this is putting a source of light over here and seeing what type of shadow this radius vector casts over here as we go through our degrees angularly, as we go through our degrees linearly here. So we're going to start out at 0 degrees. At 0 degrees, the shadow that this radius vector would cast, if there was a light source over here pointing in this direction, is 0. Let's rotate this through 90 degrees. At 90 degrees, you're going to see the complete dimension, the complete length of this shadow, and there it is. At 180 degrees, the shadow would cast 0. At 270 degrees, it would cast a negative radius vector length, which is the peak value, don't forget. And back at 360 degrees, you're back to 0. So I want you to notice one way of looking at these sinusoids is in terms of this frequency, which is what we've done up to now, or angular velocity. This angular velocity is pretty important in electrical engineering. The velocity with which the radius vector rotates about the center is called the angular velocity, or angular frequency, or angular velocity, and it's represented by this omega. Omega is equal to distance divided by the period. Well, you know what the distance is. The distance from here to here in radians is 2 pi. 2 pi radians is 180 degrees. And what's the time element takes to do that? It's a period t. That's a period t to rotate that radius vector 360 degrees. There's an equation for omega. Omega is equal to distance divided by the period. 2 pi divided by the period in radians per second. Now that's useful, but let's take a look at the next page. Since the period is 1 over f, we make the substitution, and this is the most important equation right here. I want you to circle that or put a rectangle around it. Angular velocity is equal to 2 pi f. You take 6.28 times the frequency, and you're going to get what the angular velocity is in radians per second. Keep in mind as we go through this that the conversion between degrees and radians will be very important. 2 pi radians equals 360 degrees, so pi radians is 180 degrees. So if you have 30 degrees and you want to convert that to radians, you just have to form the ratio. Do you want 2 pi? Do you want pi over 180 degrees? You want 180 degrees over pi radians? Well, you want to cancel the degrees, obviously, with some dimensional analysis here. So what we want to put is pi radians at the top and divide that by 180 degrees. The degrees will cancel when you end up with radians, and vice versa when you want to go from radians to degrees. That's the important conversion right there. It's just a matter, do you write it as pi over 180? Or when you make your conversion, do you show that as 180 degrees over pi? Keep it in mind, pi is radians. Radians. Pretty easy to convert. The general expression for sinusoidal voltage or current, this is a general expression, so I'm not going to call this V right now. I'm not going to call this I. X of t is equal to x peak, or the maximum value, times the sine of omega t plus some phase angle. This is the general expression. It's going to be very easy to understand. I'm going to give you some examples in a minute, but here's a general expression. Why would you need that? Because if you have a sinusoidal waveform that maybe looks like this, or looks like this, or looks like this on the next page, if you want to start analyzing the circuit, you have to put it in terms of a mathematical representation. And I'm going to show you how to do that right now. So here's the general expression, and how I'm going to get specific now. The voltage with respect to time is equal to V max, or V peak, times the sine of omega t plus some angle. Now that angle is phi sub V. I should have a little v in there, because that phase angle, you'll see where this comes into play in a minute, that phi sub V is associated with the voltage. It's an angle associated with the voltage. And this current with respect to time is equal to I max, or peak, times the sine of omega t. You know how to calculate omega. If you have period or frequency, I just gave you two equations to do that, plus phi sub I. This V of t is in volts, and representation for I of t is in amps. Other waveforms need many sine waves to combine together to describe them. So if you have a square wave, or a rectangular wave, or a pulsed waveform, you can't show it with one sinusoid, obviously. Okay. Fourier series will tell you that you'll need multiple sine waves at different frequencies to be able to represent a square wave. or a rectangular wave, or a sawtooth waveform. But that's not the case with the sinusoid. It's pure. Let's work some examples here real quick. I want you to take a look at page 22. I want you to write a mathematical expression so we can start analyzing a circuit if the voltage via T is equal to this. There's a peak value. It's symmetrical. There's no DC shift here. This is 0 volts here. And the period is 16.67 milliseconds. I want you to write that as a sine equation. And I want you to take a look at this waveform. And I want you to express this in terms of a mathematical equation. And I want you to take a look at this. This is a sine wave. This is a sine wave, but it's inverted. Shifted by 180 degrees, if you will. And this is a cosine wave. Now, you don't have the answers here. But I want you to take a look, stop the video, take a look at each one of these, look at the past 2 pages, and see if you can come up with this on your own, see if you can come up with that on your own, and see if you can come up with this on your own in milliamps. It's important. It's important you're able to take sinusoidal waveforms. When I say sinusoidal waveforms, I include cosine waves, and be able to take them from the oscilloscope picture that you see and put it into a mathematical form so we can analyze it. Phase relationships. Let's talk briefly about phase relationships. Up to now, if you take a look at the pure waveforms, we didn't have any shift on the waveform. In other words, the waveform's positive slope went through what we labeled time 0. Look like this. Most of the sine waves you see, or cosine waves you see, are at that point right here in time, starting at 0 seconds. Well, what if you shifted a little bit? That's called a phase shift. If you shift that waveform to the left, you see that little angle right there? Whatever that angle is, it's a positive angle. If you shift that waveform, look what we did here. That sinusoid waveform was shifted from here to here. It was shifted back in this direction. That's called a negative phase shift. Now, I don't want you to look at it in terms of anything to the left is negative and anything to the right is positive. No, the way you have to look at that is you have to be over here on this side, and you have to look at that waveform coming towards you. Remember that radius vector that rotated counterclockwise? Well, these waveforms, when you look at a sinusoidal waveform like this in the time domain, or in this radian domain, if you will, on the abscissa axis, you have to be over here and you have to look at it coming towards you. That waveform's coming towards you. So that's positive. That's a positive phase shift when it's shifted to the left. Remember that. And when it's shifted to the right like this, it's a negative phase shift. A couple equations I want to point out to you, which you're going to be using very shortly, and you don't have these, but I'll show them to you real quick. You had this in trig. The cosine of an angle is equal to the sine of the angle, and you have to add 90 degrees. Well, if you take a look at a cosine waveform and a sine waveform, and you're standing over here to the left of this vertical axis, I think you'll see that the cosine waveform is ahead. It hits you first. That cosine waveform you're gonna see its magnitude hit you first, and then sometime later you're gonna have a sine wave. So what do you have to do to the sine wave to get it to catch up to the cosine? You have to add 90 degrees. That's one way of memorizing this. In terms of the radian frequency, the cosine of omega t is equal to the sine of omega t, and you're adding pi over 2. Pi over 2 is 90 degrees. These are really the same equations. What about sine? Sine is equal to the cosine of the phase angle minus 90 degrees. Why? Because you have to slow the cosine waveform down. You have to move it back to the right, so it'll be a cosine wave. You either memorize these, or you think of it in terms of, what do you do to the sine if you want to get the cosine? You better add 90 degrees. What do you do to the cosine if you want to get the sine? You have to subtract 90, because the cosine is ahead of the sine wave. And here it is in angular velocity. Sine of omega t is equal to the cosine of omega t minus pi over 2. Pi over 2 radians and 90 degrees are the same. These are identical equations. So that's all I'm telling you here. The terminology is based on looking at that equation. The cosine leads the sine by 90 degrees. Draw the waveforms and you'll see that. You know how to draw a sine wave, you know how to draw a cosine wave. And here's the other equation. Even though these units aren't the same, the author uses it like this so you can get phase angles real quickly, independent of the angular velocity. It's the angle between them that's going to be important. So you're going to see, even though the units here and the units here are different, this is the way we're going to represent it. So up here, when you look at that equation, the cosine leads the sine by 90 degrees. Down here, look at this equation. Another way of saying that is the sine lags. It lags behind the cosine by 90 degrees. Lead and lag are terms that we're going to use a lot from here on out. They're used to indicate the relationship of two waveforms with the same frequency. So get used to the terminology lead and lag. And here's some other equations. You know that the sine of minus omega t is the same thing as negative the sine of omega t, and you can look through these. If you have a negative in front of the sine of omega t, either add 180 degrees or subtract 180 degrees to get rid of that negative sign. Same thing down here. That negative sign that you see in front of the sine or cosine, it's just a 180 degrees phase shift. Think of your trig and you'll understand that. Let's do two example problems real quick. Example problem number 3, just to show you how you use this stuff. This is on page 24. Using an oscilloscope, let me show you one more thing I wanted to point out. Besides memorizing these, I always give the students this. I always show them this. If you can look at a little figure here and label this axis cosine and label this the sine. And then that radius vector rotates in this direction. Don't forget that radius vector is rotating in this direction. And if you're standing up here somewhere, oh, geez, let's make you there. There you are. You're standing right there. What's going to hit you first? The cosine. What hits you second? The sine. And notice the sine is 90 degrees behind the cosine. If you're at the sine, you want to get to the cosine, you better add 90 degrees. So think about it. If you're at the cosine, you want to get to the sine, you better back it up. You better subtract 90 degrees. Very useful little figure that may help you out. Okay, problem number 3. Using an oscilloscope, the following voltage waveform has been measured across this capacitor here. So here we have this simple circuit, series circuit. We have some voltage via T out here, and it's a sinusoid, and then we have a 50 microfarad capacitor. So you get on the oscilloscope and you see this waveform. This waveform goes up to 30 volts, down to minus 30. There's no DC phase shift here. There's no DC offset here. This is 0 volts. It's symmetrical. And the period from this point to this point is 20 milliseconds. Express that in terms of a sinusoid. Try that and see if you get this. Don't just copy this down. See if you can say via T, this voltage here is equal to the voltage across the capacitor. It's the same voltage. The rise has to equal the drop. Remember, Kirchhoff's voltage law works for AC circuits too. This rise has to equal that drop, so these have to be identical here. So the voltage with respect to T at the source is equal to the voltage across the capacitor, which is 30 times the sine of 314 T plus 0 degrees. There's no phase shift. How do I get that 314? It's omega. Omega is equal to 2 pi times F, or 2 pi divided by T. That's how I got that. So once you get this, you're going to know from a previous lecture that the current in the circuit is equal to C dV dt. You already memorized that. Take capacitance times the derivative of that voltage, and here you have the here's you have the current in the circuit. I drew a picture of that current waveform down there. I took this and there are two different scales here, don't forget. I'm showing current, and then this other one is voltage, and the voltage scale is going to be different from the current scale. So keep that in mind here. But here I have my current waveform, which is a cosine. Here I have my sinusoidal waveform, which is a sine wave. And if you're standing over here, what's going to hit you first? Well, the current's going to hit you first. Notice that the current is leading the voltage by 90 degrees. Well, why? Why is that current here leading that voltage by 90 degrees if you're looking at that waveform as you stand over here? And now waveforms are coming toward you. Well, you know the reason why. Because the voltage cannot change instantaneously across the capacitor. It can't keep up with the current. So the current's going to lead the voltage across the capacitive circuit. Now, if you don't like drawing these waveforms, which I don't recommend, I would just take this, and since we took a look at the voltage, since the voltage here was in terms of the sinusoid, we have to compare apples to apples. We have to convert this to the sine wave. Well, I just showed you how to do that. You just have to add 90 degrees. So now I can say that the current, in terms of sine, is 0.471 times the sine of 314t plus 90 degrees. And that's in amperes. Now I'm comparing this, which is the current in that circuit, to the previous page, which is the voltage. And I think you can see that the current reaches its peak 90 degrees ahead of the voltage, because voltage cannot change instantaneously in a capacitive circuit. I'm going to introduce a phasor diagram here real quick. We'll talk about it later, but take a look at it here. I'm just going to take a look at the two voltages, the voltage and the current. The current's at 90 degrees. The current's at 90 degrees, so I'm just drawing it. Don't worry about the magnitudes of these vectors here. There's your IC at 90, current at the capacitor, 90 degrees. Here's your voltage capacitor angle. It's 0 degrees. Look at the previous page. It's 0 degrees here. And I want you to notice as that radius vector rotates counterclockwise, the current's ahead of the voltage. Another way of looking at that is the angle associated with the voltage is 0 degrees. The angle associated with the current's 90 degrees. You always take the voltage minus the current, and you get a phase angle that's minus 90 degrees. That's going to be pretty important. When phase angles are negative, when the difference between the voltage and the current angle, and you always take the angle of the voltage minus the angle of the current. When it's a negative angle, you're going to see it's always a capacitive circuit. If it's a positive angle, it's always an inductive circuit. We'll talk about that later. Example number 4. I want you to work out example number 4. Keep it in mind, it's an inductor and you have current. This is current with respect to time. There's the waveform. I put it in terms of a sinusoidal equation for you here. Notice there's no angle down here, so I didn't even write the 0 degrees in. Work this problem out. See if you get this solution. See if you get that solution right there. That's what you're going to end up with, comparing apples to apples. I converted that cosine to the sine. There's the representation for the voltage across the inductor. Here's representation for the current. We already have that on page 26. Make sure you can do these on your own. And I did a phasor diagram. And notice the voltage leads the current by 90 degrees. Why? The voltage leads the current by 90 degrees because current can't change instantaneously through an inductor. It's always going to be behind. You could say the voltage is always going to lead the current in an inductive circuit, or you can say it this way. You can say the current is always going to lag the voltage in an inductive circuit. In a purely inductive circuit, that angle is 90 degrees. Notice I calculated my phi sub v was 90 plus 90. My phi sub I was 0. Always take the difference between the angle of the voltage and the angle of the current, and you get a plus 90 degrees. When it's a positive angle, it tells you you have an inductive circuit. 90 degrees means it's purely inductive. You're going to find out in 2 weeks when it's between 0 and plus 90, there's a resistor involved. And the closer you are to 0 degrees, the more the resistance is playing a role. The closer to positive 90, the more the inductor's playing a role. If you look at the capacitive circuit, The closer you are to 0 degrees, the more the resistors play in the role, and the closer you are to minus 90 degrees, the more the capacitors play in the role. Here's a little note that you might find useful. I don't find it very useful, but in some programs they give it to you. You'll hear people talk about Eli the Iceman. Eli the Iceman. Little note to help you to jog your memory. The source of EMF, the voltage leads the current in an inductive circuit. The voltage leads the current, it's in front of it, in an inductive circuit. And you know why, think of that. And here, the current leads the voltage in a capacitive circuit. Eli the Iceman. The voltage leads the current in an inductive circuit, and the current leads the voltage in a capacitive circuit. And I'm going to hold over this application until the next video lecture. That concludes this lecture.